on commotion is on electron coupling, ejecting free conduction electrons in the copper. And because I think the mechanisms are so closely related, I'm of the opinion that the X-ray energy we see, if we could measure accurately the electron energy, the upper end of the electron energy, I think, would be correlated with the X-ray energy. So we wanted to test the conjecture of X-rays, conversion of vibrational energy, and nuclear excitation. Well, this experiment doesn't tell you that that's what's going on. It tells you a consistency with it, gives you more information than you had before, but it's not proven without any question. But it's getting there. Vibrational resonances. So we observed X-rays near 1.5 keV, correlated with mercury, consistent with upconversion conjecture. Electron emission is not correlated with mercury, and thought to be upconversion of vibrational energy to promote free electrons. And finally, oh yeah, collimation. We have not done a collimation test on these X-rays. I'm of the opinion that they are collimated, mostly because of Carboot's work and because of Vyssotsky and Kornilova. And we would love to measure the collimation. It's an important thing to do. Well, it's easy if you have a program, if you have funding, if you have support, if you're actually allowed to work the condition. I mean, there's no funding for this work at SRI. Things can't happen without a contract. We're interested in getting a version of this up at MIT. In fact, I think somewhere there's a volunteer who actually liked to do this. We have willing hands who would love to carry this further. And I have a credit card that hasn't maxed out yet. Afford a little bit of equipment. Anyway, questions?
The new lines that you're exciting are, of course, fascinating. The question is, can you get any additional information from the line profiles? They certainly don't look like Gaussians or delta functions.
The line profiles observed here are dominated by instrumental broadening. We don't have a good...
convoluted by the instrument itself.
Yeah. I have a model, a theoretical model for the line shape, which is valid when the energy transfer is above the transition energy. I didn't have a model, I haven't worked the model out for the other case, and I actually wasn't expecting to get a sharp line that was moving, and I don't actually know whether the model's going to be happy with that or not, but that's what the measurements seem to show.
What did we say the collimation is due to?
I'm of the opinion that collimation is due to phase coherence. So within the conjecture that vibrational quanta are being upconverted, if the vibrational quantum is uniform over the surface, like in the L1 and T2 modes that we're exciting, then excitation would have phase coherence if upconverted by vibrations. So the collimation in the other experiments is consistent with the mechanism. Like I say, we don't know about this experiment yet.
Can you say anything about the Q of the resonance?
I can say an awful lot about the Q of the resonance.
Okay.
I can go on for hours about the Q of the resonance. If the metal were hanging magically out in vacuum with
Yes.
nothing around, then
Yes.
the Piperd loss would dominate the Q of the resonance, and it would be very sharp. It would be like 1 in 500,000. That's, of course, not what we observed. So because the foil is clamped down and there's resonator and other things around, the loss to the resonator and the other things around is clearly giving us a broadening. However, when the electron emission occurs, I'm of the opinion that the power given to the electron, if it's coming from the vibrations, is the dominant loss in the system, and that's going to determine the broadening of the line.
But this was in air, right? So, yeah. So that's going to broaden it by a lot.
The X-rays?
No, the air. The air. I mean, it's vibrating in air, right?
Right.
Or is it a vacuum on?
No, it's vibrating in air, but
Yeah.
megahertz to air coupling's not very efficient, the impedance mismatches.
Is there any scenario for these frequencies occurring in Cartwright's experiment?
In fact, there is. The way it works is car boots foils are thinner than what we use. So car boots frequencies are between, in my view, between 100 megahertz and 250 megahertz. So I came and I said, Fran, you know, I want to do at least 100 megahertz. Fran says, 10? I said, 70? 20? We ended up at 30, 35.
On the collimation apparatus diagrams, the cathode was always planar, and the collimated X-rays were shown going perpendicular to the cathode. Have you done experiments with different shapes so that the field would not be as uniform?
Okay, your question is a great question. There's a few different answers to it. If you look at car boot's data, car boot has a small number of pieces of data which are consistent with having the fundamental vibrating. So the collimation is coming and making a very tiny spot, well resolved sub-millimeter spot some significant distance away. The other traces seem to look on the spectrum like they're moving. You scratch your head and you say, why in the world should they be moving? Well, if you have a fundamental, and if you have excitation of surface transverse degrees of freedom, and even if you got more than one of them, then the point moving is going to have some sideways moving, which is going to make something going collimated be slightly one way or another. So car boot's data, in my view, already shows exactly that. Vysotsky presented data where he ended up doing some focusing X-ray. And I want to give him a plug for it. That's some of the most exciting data that I think I've seen. Sean.
Okay. I think a simple experiment. I suggest, if it's possible, to make experiment with static different gas from air, for example, argon or nitrogen, helium, just to rule out possibility there is some interaction with the air or the nitrogen.
As it turns out, at SRI, right now, Fran is standing over the device. There's a tank of neon hooked up, pumping neon in.
Yeah,
And the idea is that
very quite
we're actually
easy. Or
hoping-
you put just in the plastic bag.
Yeah.
Really, very simple improvements.
We were doing it not for the reason you suggested, but neon happens to have an absorption edge at 875 volts, and we were hoping to get a confirmation of X-rays from having an absorption feature imprinted on it.
Okay.
What kind of a different shape of the collimation would you expect if you excited, say, a harmonic mode in the drum head with a
Okay, the drumhead mode is at much lower frequency, and so it's going to be harder to get kilovolt X-rays with the drumhead mode, in my view. We didn't find the drumhead mode in the experiments so far. But if you imagine driving it at other frequencies where you have
exactly
stuff going on, we've seen evidence of that already. I think we have spectra that shows two peaks, which you might argue comes from one mode being excited at the same time as another mode being excited. But with respect to collimation, given that we have the ability to excite different modes as we choose, we should be able to direct it as we like if it's really collimated and it works that way.
Is the excitation, the X-ray frequency, is it an integer multiple or half integer multiple of the driving frequency? Is it a harmonic of the driving frequency?
Is 1565 electron volts an odd multiple of 1.3 times 10⁻⁷ volts? Is this what you're asking?
Well, do you have the resolution to see if it's a harmonic?
So the question is it 10 to the 10th plus 1, 10 to the 10th plus 3?
Well, I didn't know it was 10 to the 10th, now you're telling me, maybe it's not a good question, but that was, what is that number? I mean, and what is the resolution? I mean, if it's a high Q cavity, if you go to a vacuum, say, you get a very high Q.
In this experiment, we don't have the resolution to tell.
But could you? I mean, could you do
in some other experiment, sure. For example, if, is it FILE0147 that has a transition of 7 volts, and if you cranked up the frequency to much higher, then you could start having the numbers be manageable. It turns out there's, at some other point I'll be talking, there's another system which seems, in my view, to be showing this effect. It's not vibrational, that you can resolve it, and the data seems to show exactly that resolution. But this is a story for another day. Sure.
There was ICFF 10, yeah, sure. I had an experiment with Bob Smith, he's here someplace.
Yeah,
Anyway.
George, I can't hear you, what you're saying about it.
Yeah, okay, I'm just saying, we, did a replication of Caribou's experiment, although he didn't like our technique, but, 2 comments about it. One, we did try to measure the collimation, and it was far from being diffraction limited, it wasn't good at all. And certainly you don't have a laser, as he claimed. He insisted we were doing wrong, or we wouldn't have. Second thing was, this mercury, I don't think we had very good, vacuum, I don't think we had mercury in our system.
Yeah.
We'd have to go back and worry about that.
You know,
Well,
mercury
my question might be, if you get electron emission when you
Not
put
good.
mercury in.
We do.
Yeah.
But again, the electron, if the mercury's on, as near as we can tell so far, the electron emission drops a little bit. Probably because whatever's on with the mercury is blocking the X-rays, or the electrons coming out. So, with respect to the mercury, the conjecture was parts per million contamination in Carboot's experiment, sort of environmental levels contamination that might be found like anywhere. So it's not, nobody thought that Carboot was pouring in mercury to get the effect, but in this experiment the X-rays seem to be correlated with the mercury being there.